everyone. Just a little intro. I work at a company called Innova Technologies. We're based in Adelaide, although this talk is about, I guess, my experiences and opinions. So yeah, just keep that in mind. This is kind of, I guess, my talk rather than their talk. So a little bit of an introduction about me and what I've been working on in my experience. So I've developed software for a bit over 7 years now, and that's kind of been split between satellite software, so software that's currently operating in orbit, modems, so software that talks to the satellites in orbit, mission control systems, so how we actually control and command the spacecraft, and mission planning systems. And I guess one area that I kind of left out there but integrates into the rest of them is operations, so automating the operations of the spacecraft so that we can run them efficiently. So a little bit about these images that kind of some of the things I've collected over the last few years. The one on the left there is the first spacecraft we put in orbit, so that's been up for a bit over 12 months now. The one in the middle is a rocket that we integrated some of our hardware onto that was meant to launch out of Port Lincoln in South Australia. And then on the right is one of the test facilities in Canberra. So the talk I've tried to make quite broad and then explain, I guess, some of the space relevant information as I'm going through. And that's just to provide context around the industry, what sort of software is relevant, and how open source ties into all of that and kind of enables us to develop these systems. So just a bit of an overview of the space industry. In case you're not aware, Australia is quite new in this industry. I guess we have played in space before quite a while ago, maybe like 60, 70 years ago. But then there was a pretty large period of, tens, like probably, 40, 50 years where we weren't doing a lot in the space industry. So we've developed our own space agency within the last kind of 6 years, and that's grown the industry, but we're still very new on a global perspective. And what this means is that there's no heritage to carry over from, which is, I guess, a good thing and a bad thing. The good things about it is that we can take really modern approaches to how we develop the hardware, the software. The bad thing, I guess, is that we haven't learnt from the mistakes that have happened over the last, 50 years. And so, we're probably learning some of those mistakes, firsthand as we go through this process. One big area is government funding is tight. So I was just looking up some stats before this talk to try and understand the scale of this. So the Australian space budget is 1,000 times less than the American space budget. And that means that we need to do things differently here. And that's, I guess, one of the areas where open source software plays a big role in that. You can see that as I go through this and I'm listing off, libraries or packages or frameworks that are relevant, a lot of those have been, I guess, enabled through, NASA or the European Space Agency, and they kind of allow us to be able to develop these systems, efficiently while still kind of, contributing to the overall open source software community. So one of the other things that's a big consideration in the space industry is a high level of assurance. It takes millions of dollars to get a satellite into space, and so it needs to work, like first time, 100%. There's, if it gets up there and it starts boot looping, you've just got space junk, basically. And so flight heritage is usually a key metric for this, and it's kind of like one of the areas that I guess I'll touch on with some of these open source projects, that if you're looking at, frameworks developed by NASA and that's been already in operation on a number of missions, then that kind of helps you, I guess, have confidence that your system's going to work once it gets up there. So some of the market trends that have affected space, this is just a high-level view, and then I'll dig down a little bit more into the interesting technical areas. But space, a lot of the stuff that happens in space, or the hardware that is in space, is basically no different than IoT or automotive stuff, right? And so as IoT has grown in popularity over the last, 10 years, all of that, a lot of the development or technology that has come out of that is all relevant to the space industry. The hardware that goes into space is a lot of the time the same thing that's like, in your Toyota Camry, like powering the head unit or whatever. The hardware and software solutions are very similar, although there are some differences, just because you're talking to, the hardware that's 500 k's away, and you get to talk to it twice a day instead of, 24/7 type thing. Satellites are getting smaller and cheaper. So there's this thing called new space, which is about doing space differently. It's about doing space in a smaller way, more agile way, more capable way. And that's kind of really been happening over the last kind of 10 years, where they've had these new form factors of satellites called cube satellites, which are standard form factors, which means you can launch them way cheaper. And so the launch costs have come down over 10 times since Elon Musk has developed, the boosters that can land themselves now. So that's been a significant decrease in costs, which then means that there's a lot more satellites going up there. They become more accessible. There's new technologies that are reaching space. And space is kind of increasing globally, I guess, in funding. Everyone, I guess, acknowledges that things like, GPS or environmental monitoring are really important things to understand. And so there is a trend towards more funding for the industry. So now a bit of an overview of what a satellite system looks like. Sorry for the average diagram, I'm just not very good at diagrams. But so looking at this, you've got your satellite, so that actually, gives your system its purpose. So that could be something like capturing images of the Earth as it flies over. It could be a comm satellite like Starlink. There's various numbers of scientific type payloads that could run on there. So one of the missions I was involved in had a X-ray gamma ray detector to measure like black holes colliding in space. And then you need a way to be able to talk to that satellite. So the satellite will pass over a ground station, kind of depending on its orbit. It might be 20 minutes throughout 24 hours of the day. And so you need a way to actually communicate between the satellite and modem. Unfortunately, the comms to the satellite isn't quite the same as plugging in the RJ45 into your laptop. You drop a lot of packets. It's very unreliable. And so just kind of slapping TCP on that link isn't going to work. And so you need a modem that contains specialized software that's, I guess, suited for those kind of like low reliability links to make sure that you can efficiently communicate with satellites, seeing as you only see it 20 minutes a day. So then from there, a standard architecture would be that, now that we're in the 21st century, we've got internet running to our ground stations, and they flow back into our mission control, mission planning server. So depending on, I guess, who's building the system, that could be running in the cloud, it could be running, on premises, and then you've got your, user terminal that connects to that. Yeah, that's pretty good overview. So now just drilling down into a satellite, I'm just trying to build up context, I guess, before I start going to the software side of things. But what's inside a satellite? So when you look at a satellite, you've got kind of like two parts of it. One is the platform and one is the payload. And the platform is all of the stuff that you need for it to be a satellite in space operating. And the payload actually gives it its purpose. So as you would expect from the platform, you need things like solar power, battery power, As you go around the Earth, you're going to go into eclipse. It's not going to be able to see the sun. And so the battery power carries you through that period and make sure you can still operate it in that area. You need a command data handling system. So that's doing the ground comms that we were talking about. So basically a modem on the spacecraft. And then it also does things like autonomous operation, as you don't have control over it or commanding to it 24 hours a day. It needs a system to autonomously be able to command the whole system and collect telemetry from it. So think of it, like all of the logs that you might get off a server or something like that. You need to collect all that stuff, beam it down to the ground station so that if weird stuff happens, you can figure out why. And then you've got what's called an attitude determination control system. So this is how the satellite orientates itself. So if you want to take a photo as you're flying over Adelaide, you need to be able to point, your camera at the ground as you track over it. And so the attitude control system, it figures out what orientation it is in. It figures out where it is around the Earth, and it controls its orientation and may also have a thruster integrated into it. And then there's the payloads, and they're kind of, like the examples I was saying before, there's a number of different reasons or payloads that you might have or purposes for the satellite. And I guess the most popular ones would be Earth observation and communications. Obviously Starlink is just really taking off at the moment. So now looking at what open source software is relevant to the satellite side of things. And maybe some of these will definitely be familiar. But some of them you've probably also come across through like IoT applications and things like that. So FreeRTOS is a kind of bare bones operating system. So some of the software that you need to run on a spacecraft needs to be real time. You need to have control systems that run in a deterministic way, and estimation algorithms that need to run with particular frequencies. And so that drives people towards real-time operating systems that have that deterministic behavior. Although Linux also has some patches, or I think it's now in the mainline kernel, preempt RT kind of parts of it that allow you to run more deterministically. So FreeRTOS is a real bare bones operating system. ChibiOS is kind of like bare bones with some hardware abstraction layer on top. So it kind of gives you the next level up to get started. And Zephyr is one of those projects that has really kind of taken off with IoT coming in. So you can see as part of that, it's got kind of like Bluetooth and MQTT protocols integrated into it. But that would also be quite relevant for systems that you might run on a spacecraft. There's a lot of kind of complicated algorithms and like linear algebra and mathematics that needs to run in order to determine its orientation, its location on the Earth, calculate the control signals that need to go to different aspects of the spacecraft. And so Eigen is like a really useful kind of like library for that. It kind of almost makes it bearable to do those sort of things in C++. Whereas, if you look at Python or MATLAB or something like that, it's far more enjoyable to do something like linear algebra. And then looking at the more spacecraft-specific side of things, there's a couple of flight software frameworks, and these are the things that have been built over a number of years and provide that kind of like flight heritage background, where there's a thing called CFS, Core Flight System, which is built by NASA, and that's all open source, and it provides you like a really good framework to get started on like what systems do you actually need for your spacecraft. The newer version is called F Prime, is also by NASA, and that's probably like a more modern approach, maybe a little bit lighter weight, more designed to run on things like microcontrollers, where CFS might be maybe a little bit large, depending on what sort of microcontroller platform that you're going to use. I think one of the things to talk about here is what I touched on originally with the the good and the bad thing about being new in the industry is we can do things differently and be really modern in how we approach these problems. Whereas I guess, NASA has the way they've been doing things for, 40, 50, 60, 70 years. And you can kind of see that in some of the library. If you dig through it, you might find that it's a little bit strange. And I think it's kind of like some of that carryover. I'm sure it's like a very robust framework, but it looks quite different to, what you might expect of modern software. So now looking at the next part of the system, the modem and ground station. So this is usually, you have basically your ground station, which is an antenna with a rotator. That's an antenna on the right. And then that hooks in basically an RF signal back into a modem, which is going to translate it from analog RF signals into a digital signal, which hopefully is something like, Ethernet on the other side. So GNU radio is a very popular framework to get up and running with communications. A lot of the comms needs very high rate processing. So you imagine that you've got, maybe 50 megabit or something like that coming down. That doesn't sound very fast, I know. But when you start applying these algorithms on top of it, it's difficult to process even on something like a very high-powered PC. And so GNU radio is really good for being able to put those algorithms, running them efficiently on something like a software-defined radio. One of the other projects that's kind of a standout with actually being open source hardware is a company called Planet, which is probably the largest Earth observation satellite company. So they've got hundreds of satellites taking images of the Earth every day, and they open source their radio design. And so this is kind of like one of the projects that gives you a kind of example of what sort of hardware is, operating on some of these satellites. So the whole radio costs $50 to make. It's $50 worth of parts. The actual radio transceiver, I think, is like, $2 or something like that. It's the same thing that you probably find in your car keys. And that's operating on hundreds of satellites in space right now. So they've open sourced their hardware and provided a very like a simple software project to get started. But it's a good kind of starter to have that like flight heritage, I guess, as part of your system, particularly for the radio, which is pretty core to have working. All right, so this is one of the other areas I want to talk about with the mission control system. So I took that photo last year. That was the mission control room for Apollo 11. And that's kind of, I think, what a lot of people picture still across the industry is, you need 100 monitors with 100 people looking at them all at the same time to operate a spacecraft. But that's not the case. You don't need something like that. And you can see like the slow modernization of the space industry as it moves towards, the same sort of technology that's being used widely everywhere else. So transitioning from dedicated hardware to web apps, which just makes sense. Mission control remotely via the internet. So, ideally you'd want to be able to control your spacecraft sitting on the couch. That's, why not? Like everyone else is, doing their applications through web apps. So why should space be any different? And then ground stations are starting to move towards this as well with APIs to actually drive automation through it. So it seems a little bit crazy that this is like, we're still talking about APIs being part of a ground station, but it's just a slow industry to transition into a modern approach. So the other thing, I guess, is now with APIs in the ground stations, people are even talking about abstraction around ground stations. So you've got a number of different ground stations you might want to integrate into, and people are talking about, well, I can provide a library that means that you don't need to write any sort of drivers or, different code for different ground stations at that layer. And ultimately, this all leads to automation-driven systems, which, when you start thinking about Starlink, there's thousands of satellites. If it's not automated, then someone's going to have a really bad time over there. So it just needs to be automated. And a lot of these systems, like it sounds like, operating one satellite should be manageable for a person, but when you start like actually planning it out and trying to figure out, okay, so we need to take an image when we fly over this area, and then we need to process that image, and then we need to try and downlink that so that we don't fill up our storage too much. And then we also need to do all these other operations, throughout the same 24-hour period. It very quickly needs to transition towards automation because there's just no other way to handle it. And so there's a couple of mission control open source projects out there. One of the key ones is OpenMCT. So this is also provided by NASA, and it's a really nice modern interface. And I think it's when looking at some of these projects, it's kind of interesting to think about like how they've cut their part of the solution. So OpenMCT is primarily like a front-end framework or front-end library, so it's built on Angular and Vue, but it provides a series of components and kind of like a way of building a mission control system, kind of like a thought pattern to guide how you build it. And I think that's like a really nice way that they've thought about the problem so that a lot of the industry does things differently from like a commanding point of view, from a telemetry communications point of view. And so limiting the open source library to just looking at the front end components and you having to build your own back end then means that everyone has the flexibility to kind of do things their own way, but still kind of leverage, the development that's happened there. Another one out there is called YAMS. Yet another mission control system, but that's more of a holistic solution. So that kind of has a back end integrated into it and a front end, and that's trying to use standards. But I can't stress this enough that standards in the space industry were developed a long time ago, and when you look at them and then think about how nice like TCP is. It makes you a little bit sad. So, it's some standardization is good. All standardization could be quite limiting in some ways. So complexities of providing complete solution. Yeah, I think that's kind of like what I was talking about. Is that it's good that you can get up and running really fast, but it guides you down the path that you need to have complete standard support, even though it may not be, great from, how you want to build your system in a modern way. Cool. So mission analysis. One of the things that you need to do when you're designing your system or even your mission, I guess, is thinking about, all right, what satellites do we need? What orbits do they need to be in? How many satellites do we need? How is it going to work? How long is our satellite going to last in space? And so these are some of the tools that are quite useful for different sort of modelling or analysis when it comes to thinking about the mission. So GMAT is provided by NASA. Unfortunately, it requires MATLAB, but it is open source, scripts on top of MATLAB. And they've done a lot of the heavy lifting as far as orbital modelling, which is, crazy mathematics that's quite complicated. And so leveraging kind of that sort of orbital modelling means that you can really get a good understanding for what sort of constellation design you need for your mission early in the process. The other one is Spenvis. So this is not technically open source, but it is free. And this is provided by ESA. So one of the things that's quite different, so I guess one of my go-to catchphrases is that software doesn't know it's in space. And that's one of the key points that I say, because everyone thinks, oh, it's space, so we need to do it all different. But, it doesn't know that it's in space. We can write the software as if it was on the ground, right? One little, I guess, point around that is that there is radiation that you have to worry about. So while you know, the software doesn't know it's in space, occasionally parts of your RAM or program memory will get hit by radiation, and it will just cause bit flips. So you'll just see, you know, your variable changes from 2 to 1,000,000, and it'll just happen like that, and there's no kind of warning about it. And so you do need to design your software to be robust, but you know, there's no reason why, you know, you couldn't write Python code in space. It's just software. So with this, I guess, the SpendVis tool allows you to do the sort of radiation modeling to see, all right, what sort of environment is my satellite going to be in from a radiation perspective, and how long will it last? Because it will slowly degrade over time, being in the space environment. The radiation environment will gradually degrade the components, and it will eventually stop working. And so modeling that to understand the mission lifetime is an important thing to do. What you can see on the diagram here is so that blue-black spot is called the South Atlantic anomaly. And so that's a quite high radiation zone. This is actually plotting the magnetic field of the Earth, and the magnetic field decreases in that region, which kind of concentrates the radiation towards that area. So just a little fact. Now onto data analysis. So you want to understand all the telemetry coming off your spacecraft. You understand where the spacecraft is. You might want to say, all right, well, why did that sort of anomaly happen? Let's look at telemetry across, you know, powers, temperatures. Maybe we need to plot the satellite location as well to see, okay, well, we saw this massive temperature spike, but it only happened for 1 second, and it was right next to the South Atlantic anomaly. Okay, well, that's probably a radiation fault that's occurred. A lot of this just makes sense to do in Python. Python's really good for data analysis, obviously, and I am in love with Plotly and Dash. The charts that they produce are so pretty. It's hard to go back to matplotlib once you've actually started playing in Plotly. And so this thing on the right, the dashboard on the right, is provided open source from Plotly, and it's a satellite dashboard, so it kind of gives you a bit of a picture of things that you can do. As far as, you know, working with the data, Pandas is a great library. You know, you can do, a lot of it is tabular data, so it allows you to do a lot of the long-term trend analysis, you know, statistics, modeling, all that sort of stuff. And Cesium is a great tool for sort of 3D visualization. So the image I've got there is a screenshot of one of the tools that we've developed to plot, you know, where the satellite is at the moment. And really having that visual understanding of where the satellite is, what it's doing, and what orientation it's in is really important to get an intuitive understanding of what's happening. So now looking at kind of like more holistic systems that are open source. So there's a really cool project or group called SatNogs, and it's a global network of open source satellite ground stations. And so the image you can see on the bottom left is a map of where all these ground stations are around the world, and they provide a really easy way to integrate you know, your satellite into their system so that it can track it. It's a really strong collaborative community. They're very, you can see posts on there about, you know, people trying to recover their satellites and other people jumping in and being like, oh yeah, I can try and send this command to your spacecraft, we can recover it type thing. And it also provides like an accessible way for people to get into space. So there's a large range from, you know, professional ground station operators to hobbyists that have, you know, antennas in their backyards, just picking up satellites as they're flying over. This system is like really critical for supporting satellites at you know, times where you need to understand what's going on. So something like when you get deployed out of the SpaceX rocket, you really want to understand, okay, has your antenna deployed? Are you, you know, transmitting the right data? is all that working properly? And I think that also provides like a way for the community to have more involvement, so that, you know, if you're broadcasting telemetry and getting them involved and they're tracking a satellite, you know, everyone's kind of like working together on it being a success. One of the, a couple of examples of open source, like full satellites, this one here is UpSat. So it's one of the cube satellites that I was talking about before, and kind of having that miniaturization of it. So just for context, this 2-year CubeSat will be 10 centimeters by 10 centimeters by 20 centimeters. So, you know, about that sort of size. Cute little thing. And so that was designed in Greece, and they've provided, you know, their hardware and software open source to try and, I guess, build out the community of open source satellites. They were integrated as part of the SatNogs network, which obviously makes sense based on the last slide, kind of, you know, working in that community. And it's quite impressive. They achieved nominal operation within 30 minutes, which is, very good. You can see on the right there, they've got, this is one of the cut down views of their satellite from the side. So the batteries are pretty obvious, and then you'll have solar panels around the outside. You usually have a GPS on the satellite to figure out where you are. That's kind of it. It's, a pretty compact size. Yeah. All right, onto the future of open source in space. So I think one of the pictures on here, on the bottom left but on the right, is Starship. So if you're kind of into space, you've probably heard about Starship. It's Elon Musk's new rocket that is trying to get working reliably at the moment. And so their original rocket with reusable boosters brought the cost down 10 times, and this is going to bring the cost down another 4 times. So I guess every time that the launch cost decreases, then it makes it more accessible for everyone to get into space. And so I expect, you know, this is going to drive more university and agency projects as the costs come down. However, one of the other areas of space is also going to be, I believe, increased regulation. So if you're into space, you probably also would have heard about, you know, there being a lot of space junk out there, and everyone being a bit concerned about objects colliding and a lot of debris, and then it kind of being, not possible to have any satellites in space. And definitely as more satellites get added there, it is a consideration. So I think the increased regulation is going to kind of trade off against it being more accessible, but I think there'll be increased open source kind of software come into the industry, as well as more modern standardization. I think this is going to be like one of the key areas where, if we can make space more accessible, then it means that there's, more modern approaches being taken, and there's more modern standardization and relevant software. Thank you for listening.
You mentioned bit flips on RAM. Is there any particular kind of RAM that is less vulnerable? And my other question, I'll sneak 2 questions in. My other question is, why hasn't Australia been more of a popular launch point given our distance to the equator?
Yeah. So I think with RAM, it kind of depends on what sort of processor capability you require and what the power requirements are. So it kind of depends on your satellite as to how much power you've got to play with. But if you're looking at smaller CubeSats, then they're in the order of like singular watts type thing. And so then you need to target microcontrollers, which then means that your RAM options are more limited. And so things like ECC will obviously be good for correcting those bit errors. There's also a thing called ferromagnetic RAM, which is a different type of RAM, which is known to be more radiation tolerant. However, I think the access times for FRAM also make it difficult because you want to run your program fast, but if you're going to try and use variables that have low access time, then it means that you can't. It puts a cap on how fast you can run it. There's a lot of launch options coming to Australia. So I was in Port Lincoln at Southern Launch. That was the image I showed there in the earlier slides. And so they're looking. They've got approval now to set up a launch site there. There's 2 companies I'm aware of that have got launch sites up in Queensland. So I think we're going towards, like as you say, we're near the equator, and we're also near the pole as well. We've got sea below us, which is a really good point if you're going to try and launch into a polar orbit. And so geographically, we do have like a very good kind of. I don't know, geographically we're good for launch, but that's right, yeah. The regulation is kind of slowly coming along, I guess. As the industry is young, we haven't been launching these sort of things out of Australia before, and so yeah.
Successful launches in the modern regulations.
Yeah. There you go.
Anyone else?
I understand that because of the way the US government works, everything NASA does has to be public domain. Do they actually put any effort into making it usable for other people?
Yeah, so some of the projects that we use as part of our system, like we've worked together with them, looking at bugs and features and stuff like that, and they've been really responsive. So yeah, I think NASA is like one of the key contributors to actually being able to enable this sort of thing to happen. Yeah.
Cool, thanks.
Thanks for the talk. What sort of stuff do you think the Australian space industry might be doing differently to the American and Europeans? Like, what sort of stuff are we going to specialise in, or is there stuff that we're going to be the only ones doing?
Yeah, that's tricky. So I think it's hard to pick out like a key example, but I think one of the big things is that, like, in Australia we need to do things quite differently to Europe and the US just because of the funding limitations. We need to be really efficient about how we do things, and we need to take modern approaches so that the space projects that we're looking at can operate in the budgets that we are provided. So I think it's just it's about trying to really modernise things as much as possible, and only kind of build to the requirements that are necessary, I guess, for the system. Yeah.
All right, everybody, one last round of applause for our wonderful speaker.